The Aerospace Engineering Department at Cal Poly Pomona requires the course Orbital Mechanics to have a final project, that project being a Ceres sample return mission. I, Ashton, Teimoori, the lead engineer, will be narrating this project. Our orbital trajectory designer was Benson, mapping and reconnaissance expert was Jonathan Welsher, system engineer was Iligan, and the sample recovery designer was Villasaldo. The mission overview is to send a spacecraft to the dwarf planet Ceres and obtain a sample from its surface. The sample will be returned to Earth to be further studied by scientists. The selected launch vehicle is the Falcon Heavy expendable. Our mission will utilize a Mars flyby to rendezvous with Ceres. We will perform one landing to retrieve the sample from its surface, and we will also use a direct transfer to return straight back to Earth. These are the system level requirements we considered throughout the project. We met all the requirements, and our validation methods are as shown. These are the system level objectives considered throughout our project. The objectives we met all the required objectives, and we completed one optional objective, performing a flyby. The mission life cycle shows the key events, and the mission itself will last no longer than 14 years. The launch date from Earth will be in early 2030s, and the arrival date back at Earth will be in 2043. We will spend a total of approximately 8.5 years once we arrive at Ceres. First, the team will calculate the optimal time to leave Earth and rendezvous with Ceres. Once at Ceres, the spacecraft will be placed in a sun-synchronous orbit to perform reconnaissance. After reconnaissance is complete, the team will land a spacecraft on Ceres to gather samples, and finally the lander will rendezvous with the spacecraft and return to Earth. The tools used to complete all these calculations and graph the plausible trajectories were MATLAB and FreeFlyer. The planetary information came from NASA's Horizon website, and the equations and methods used for our calculations were provided by Dr. Lantoine. Here's a list of the assumptions made for the design of this mission. To calculate the optimal trajectory from using a flyby from Earth to Mars to Ceres, we use the following algorithm. A key point is step number 4. We check the V-infinites entering and exiting Mars and make sure they're within 100 meters per second of each other. This is because since it is a hyperbolic trajectory with Mars, they have to be relatively the same. In order to calculate the mass propellant needed at Ceres for all the orbital maneuvers to land and to come back up, we use this algorithm. First, we will calculate the change of velocity needed to cancel out the orbital velocity to match Ceres' rotation velocity. Then we'll calculate the velocity needed safely to land from freefall. Add the two changes in velocities together and multiply by 2 to get the total change in velocity needed for descent and ascent. We multiply by 2 because one's for descent, one's for ascent, and we use the rocket equation to calculate the mass of the propellant. We also created a MATLAB script to iterate through all the possible trajectories from Ceres back to Earth. First, we obtain the positions and velocities of Ceres and Earth. Then we solve the Lambert problem from Ceres to Earth. We check to make sure that the V-infinite at Earth is less than 10 kilometers per second, so we meet the mission requirements. Then, if that is true, then we calculate V-infinite at Ceres to calculate the delta V needed to insert into the return trajectory. And once we calculate that, we put it on a pork chop plot to find the minimum delta V. After running through all the different iterations, we concluded that we can deliver a max payload mass of 2,816 kilograms, including fuel, to Ceres. In doing this, we will have 49.5 kilograms of unused fuel for emergencies and trajectory corrections. So we did all our calculations using the Delta IV Heavy, the gray line. We did this because it was kind of in the middle, and if we needed more mass delivered, we can increase our rocket, and if we noticed we had too much mass, we can decrease our rocket, which would save money for the whole mission. For a trajectory analysis, we studied 4 different types of trajectories. We studied a direct transfer from Earth to Ceres, we studied a flyby with Mars, flyby with Venus, and a flyby with Earth. First, we studied the direct trajectory. We noticed that we only got a delivered mass of 1,300 kilograms. A max delivered mass of 1,300 kilograms. With the flyby of Mars, we gained an extra 600 kilograms, and with the flyby of Venus and Earth, the solutions weren't so promising. With the flyby of Venus, we noticed that in order to get to Venus, we needed a retrograde burn, which resulted in too high of a C3, which yielded no results. In flyby with Earth, we were limited to our Lambert problem, which only went through one iteration, and because of this, it yielded no reasonable results for our experiment. One interesting figure we got from the data was that when we compared the direct trajectory versus the flyby using time of flight and delivered mass. We noticed that with the same time of flight, the delivered mass for the flyby would still be greater. As seen in previous slides, the Delta IV Heavy was not capable of delivering the mass we needed. Because of this, we moved up to two stronger launch vehicles, the SLS and the Falcon Heavy. We chose the Falcon Heavy because it costs a lot less and it also has a successful launch. So for designing our spacecraft, we had to look at multiple different engines. We considered 4 different engines, but the best candidate by far was the RL-10BX. The RL-10BX uses LOX and LH4 as the propellant, has an ISP of 470, and has also been used in a previous mission, the Atlas V upper stage for the Centaur. As the orbiter is collecting data about Ceres, it will be transmitting this data using 2 devices. The ultra-high frequency device, which will take 47 days to transmit, which is accounted for in our mission plan, and the X-band, which will be receiving data from Earth. These are the possible sample recovery architectures. Visuals are shown in Appendix T7, T8, T9, and data is shown in Appendix T10. Architecture 1, the whole entire spacecraft lands, collects samples, and launches back into orbit. For Architecture 2, the spacecraft will deploy a lander ascending module that will collect samples and intercept the spacecraft upon return to its parking orbit. For Architecture 3, the lander ascending module will deploy, collect some samples, return to the spacecraft, and then redeploy at a different location to collect more samples. For Architecture 4, the spacecraft will deploy a lander ascending module, collect samples, and return to the spacecraft, and then the whole entire spacecraft will land at a different location and collect some more samples. Here we have 3 figures of mirrors shown in Appendix T11. They are delta V is compared to 0.9. We have 1 sample collection and a propellant mass of 1,500 kilograms. The figure of merit chart below analyzes the architecture in regards to these parameters. Architecture number 2 has the highest weighted total, therefore being the most optimal recovery mission to meet our needs. Based upon our trajectory analysis, we decided to use a Mars flyby because it gave us the max deliverable payload to Ceres. On a side note, since the delta V needed to change the position on approach of the sphere of influence is very small, we assumed we arrived in a sun-synchronous orbit about Ceres. The major takeaway here is that our engine's ISP is 470 seconds using 1,494 kilograms of LOX LH2 propellant. Once we have arrived at Ceres, it will take 91 orbits, which is approximately 10 days to photograph the entire surface and collect topographical data using COLA. Once the data has been transmitted, the spacecraft will receive coordinates about where to land. The final design for the sample recovery portion of this mission, which is Architecture 2 because it's the only design that works, consists of the lander detaching from the spacecraft, landing on Ceres' surface, analyzing its surroundings, gathering a sample from that, launching from Ceres' surface, rendezvousing with the spacecraft, and finally departing home. Before we depart from Ceres, we will detach and leave the lander in parking orbit to shed 300 kilograms. Doing this will allow us to spare 49 kilograms of propellant mass.
Now?
Just in case. Sure. 3, 2. If we use a sooner return date, we'd only have approximately 10 days to accomplish the reconnaissance and sample recovery missions on Ceres. Because of this, we chose to use a less efficient date in terms of delta V to get back home. But this would allow us 8.5 years to accomplish the mission on Ceres. In choosing the dates that we did, the Falcon Heavy was the only launch vehicle in use today that even allowed this mission to be possible. It would give us the required mass to complete our mission while also minimizing costs. In summation, our spacecraft will launch from Earth on January 15, 2030 using the Falcon Heavy rocket. Its trajectory will feature a Mars flyby before rendezvousing with Ceres directly into a sun-synchronous orbit. Once there, the spacecraft will perform orbital reconnaissance and will deploy the lander. The lander will then gather samples off the surface of Ceres before launching and reuniting with the spacecraft. After 8.5 long years orbiting Ceres, the spacecraft will then depart, leaving the lander in orbit to begin its 1.5 year long journey back home. Finally, the spacecraft will arrive at Earth on December 13, 2043, where we will welcome it with open arms. Thank you for listening to this presentation. We highly encourage you to consider our mission.